Right. So check. Okay. Hello everyone. I'm Kanaru Isoda, a master's student at University of Tsukuba in Japan. So let me begin my presentation. Okay. So we are studying staging by MetaOCaml based approach, which uses quasi-quotation and lexical scope, allows runtime code generation, not compile time code generation, and provides type safety of program generator, which subsumes type safety of generated code. Okay, and there have been many type systems for staging based on MetaOCaml approach, these ones, and which have been implemented by MetaOCaml or its latest version by MetaOCaml. Okay, and there are many studies on computational effect in staged calculi, and algebraic effects and effect handlers provide a means to represent various computational effects uniformly and modularly. And they can represent exception, jump, state, non-deterministic choice, and so on. And they are implemented by OCaml 5, among others. So then it is a natural idea to build a type system for MetaOCaml plus algebraic effects and handlers, which enjoys type soundness. So this is the question we address in this study. Okay, so our first example is a normal program consisting of a for loop and some heavy computation, factorial 10. Okay, we can turn it to a staged program which generates a code to compute the same result. But the code is not ideal as it performs the heavy computation multiple times. To solve the problem, we want to move a code fragment of the heavy computation out of the for loop by inserting a let expression here. So let insertion was found in the study of partial evaluation, and various solutions were found. Here is a solution using effect handlers. So this is a program. This program is the same as the one in the previous slide, except that the destination of let insertion was shown by a with handler expression here. The effect handler hins implements an operation insert, which realizes let insertion. When insert is called with an argument code of factor 10, okay, it is rewritten to the body of insert here, where x is substituted for the argument. At the same time, the continuation is captured and bound to the second parameter k. And finally, we obtain the desired code. Okay. In general, the use of computational effects such as state and control operators in staging may cause scope extrusion in a generated code. Okay, let's consider this example. We change the third line so that the argument of insert contains the loop variable. By running this program, we get an undesired code which has the loop variable here freely. So the generated code does not compile, but we want to detect such an error before generating code. So how can a type system prevent this problem? I will explain the design of our type system, which statically guarantees that well-typed program generators don't cause scope extrusion. So our type system uses refined environment classifiers proposed by Kiselov and others to handle free variables appropriately. First, Taha proposed environment classifiers. His type system is a basis for MetaOCaml's type system without computational effects. And then Kiselov and others refined their environment classifiers to handle the state effect in staging. A classifier is associated with the scope of a future stage variable. The figure on the right shows various variable scopes in this example program. Gamma 0 is the outermost scope, and gamma 1 is the inner scope of gamma 0, and gamma 2 is the innermost scope. Okay, and each code type is annotated with a classifier. For example, this is a code type of int, which has a classifier gamma 0. And finally, classifiers are partially ordered by scope inclusion. In this example, we order gamma 1 and gamma 0 in this way, and the same for gamma 2 and gamma 1. Since Kiselov and others handled state only, we need some special treatment for effect handlers that can represent not only state, but also various effects, including let insertion. To understand the subtlety of our design, let's consider another example. We define two effect handlers, hinst1 and hinst2. They are almost identical, but they have different operation names, insert1 and insert2. And this program has two with handler expressions for insert1 and insert2 consecutively, and then insert1 and insert2 are called in this way. By executing the program, insert1 with the code of 10 is called here. Then a red expression is inserted at the top level of the term. Next, insert2 is called, and another red expression is inserted after the first line. So this is the result, and the result is well scoped. So this program generator is safe and should be well typed by our type system. This example is the same as the previous one, except that we have swapped the order of the operation calls for insert1 and insert2. Then insert2 is called first, and the corresponding let expression is inserted at the second line. Then insert1 is called, and another let expression is inserted at the top level. Okay, this is the result. And the variable y2 is free in the result. And we have scope extrusion again. So these examples shows the subtlety of effect handlers. Okay, our solution for the problem is based on the idea handlers as future stage binders. The scope extrusion occurred in the previous page, since the with handler expression may possibly insert let expression, which introduces binders for future stage variables. To prepare for this possibility, our type system always regards an effect handler as introducing a new variable scope or a new classifier. Let me explain the idea using the example for nested lattice session. First, we have the with handler expression. It is not a binder, but it introduces a new scope presented by classifier gamma 1 in our type system. So it is a simple idea. For another with handler expression, we do the same, and classifier gamma 2 is introduced. Okay, now I'll briefly explain how the whole term is typed in our type system. Okay. A code type is annotated with a classifier, as we've seen before, and each subtype is typed to have the suitable classifiers. Okay, let's consider the code of insert 2 here. Insert 2 requires gamma 2 as its argument between here. And it is different with the gamma 1 for variable x here. So actually it is not problem because the scope of gamma 2 is contained in gamma 1. So we can regard x has the classifier gamma 2 safely. And this is the unsafe program we have seen before. So the operation cause is swapped. So let's try to give typing in the same way. Okay, in this time we cannot regard x as the classifier gamma 1 required here because gamma 1 is not contained in gamma 2. So unlike the previous example, the last operation cause here is not well typed. Okay. The other important principle in the design of our type system is classifier polymorphism of handlers. In typing of handler itself, we cannot assign one specific classifier for it because it is determined when it is actually placed in a with handler expression. And that is why we have a universal quantification of a classifier for handler types. In this example, we give a type to a handler h-ins using an arbitrarily chosen classifier, epsilon 0. And epsilon 0 is replaced by gamma 1 here inside the with handler expression. So our calculus is a two-stage calculus with algebraic effects and effect handlers, which is equipped with a type system. We have proved type soundness, that is progress, and preservation properties. And as a corollary, we can statically guarantee that a well-typed code generator does not cause scope extrusion. Our type system is a conservative approximation for safe programs, and it can distinguish the same safe examples from the unsafe ones as expected. We plan to do more exhaustive tests for realistic programs once we establish type checking or type inference algorithms. Okay, so there are many related works, but the most closely related one is Oishii and Kameyama's work, which proposed two-staged calculus with the control operators, shift 0, reset 0. And their calculus can also implement nested let insertion as shown by this example. As you can see, our calculus provides a much simpler solution. The difference is not just the size of the code. In their calculus, we need to specify the destination of let insertion by counting the number of reset zero statically and writing the same number of shift zero. This is rather difficult in practice. And the effect handlers have named operations which are much easier for programming. As a drawback, they caused another technical problem, but we solved the problem by the handlers as binders principle. Okay, so I will summarize our main points. We have designed a two-stage typed calculus with algebraic effects and deep handlers, and we proved its type soundness. Okay, and these are the future works. Okay. So, okay, thank you for your attention.
All right, questions? I can start with a question, which is that this could be applied to OCaml, right? Because OCaml now has effect handlers and also MetaOCaml. So what are the obstacles to just porting your type system to OCaml?
So, okay, so actually our design of calculus is a little bit different with current OCaml, MetaOCaml, because
is what?
So, for example, MetaOCaml's design is a KSI quotation method, but our current calculus is based on the code combinator method. So, for example, this underline
but they're
construct.
more or less equivalent, right? I guess you can convert one to the other pretty easily, or is there a fundamental difference?
So, yeah, actually we believe this difference is not so essential, but currently,
okay.
We didn't do any work to integrate it to MetaOCaml. Okay.
Yes.
Thank you very much. Is it the case that in your type incorrect example, the type error could also be fixed by swapping the order of the handlers?
So, are you talking with this example?
Yeah.
I'm sorry, I couldn't catch your question.
So you swap the order of the first two lines?
So with handler expression.
Sorry?
Sorry, could you repeat your question?
So is it the case that you can also fix the type error by swapping the order of the first two lines?
Yeah, in this case, yes, it does fix the problem, I think.
So I wonder then whether your type system is intended to be used to provide an error to the programmer such they can then fix the order of their statements or the order fix their code, or whether the type system is intended to provide information to the first stage evaluation, which could potentially do this kind of reordering.
So your question is that can the compiler tell to the user to swap the order?
Yes, exactly. Yeah. Would that be possible? Does that make sense?
Yes, and I think that can be possible. Yeah, I think so.
Okay. Any other questions? Maybe on a more philosophical level. You know that originally MetaOCaml had environment classifiers, and I think, like you said, you have just removed them from the language.
Yes.
For practical reasons. So what do you think? Do you think they should put them back? Or do you think they pay for their complication? Right?
Yeah, hopefully currently, this currently MetaOCaml actually does not have environmental classifier, and
it no longer has them. Yeah.
Yeah. So. Yeah, but
do you think they're worth it in terms of complexity for the added benefits?
I think we have the benefits, but because we can report a more good error to the user when using some effect handlers, and it's a very complicated
right.
handler. Yeah.
So it's harder to keep track of scopes because of the effect handlers.
Yeah.
So you think they're more important in that context?
Yeah, I believe so.
Okay, makes sense. Okay, I think there are no other questions. Then we can move on to thank the speaker again.
Thank you.
Stay here for a moment. So I'm not sure whether you've heard the good news, but
okay.
We have an award for you. Distinguished Research Paper Award.
Wow.
So congratulations.
Oh, thank you very much.
Because of the light, just come over here. Yeah, okay.